So hopefully you've had a chance to think about this. You've seen a really similar equation to this before. This is basically the harmonic oscillator equation, only it depends on position and not time. It's your sort of your classic second order ordinary diff EQ with constant coefficients. And you might already know what the solutions are. You can go ahead and check this if you're not convinced. So the general solution turns out to be psi of x, right? So it turns out that we can write it as a cosine kx plus b sine kx. Oh, sorry, I'll do a sine and b cosine. B cosine kx. You can go ahead and check that if you take two derivatives of sine kx, you get minus k squared times sine. Same thing for cosine, where a and b are constants. If you've taken differential equations, you'll know that a second order diff EQ in general always has sort of two families of solutions, or two constants that you have to determine based on here some boundary conditions. And so this is what I mean by write down the most general form of the solution. We don't know what these constants a and b are, but that's what we'll get by applying boundary conditions. So let's do that next. So step 2. So the boundary conditions. Yeah. Okay. So we require the wave function to be continuous. Because if it weren't, it would be really hard to think about how the time-independent Schrödinger equation could make any sense. So, for instance, otherwise, what's d squared psi dx squared? It's not clear how we would think about any of the terms of the Schrödinger equation for a discontinuous wave function. Well, we know, right, that psi of x less than 0 equals psi of x greater than L equals 0. So that's where the potential energy is infinite. So if the wave function is going to be continuous, right? If we know that, so it has to be the case that for the part inside the box, and we've got to be able to we know we already know the behavior of the wave function here, right? So visually we know it's 0 out there. So when we're trying now to figure out what's going on inside the box here, the solution inside the box has to sort of glue together onto the ends of So inside the box, psi of x equals 0 equals psi of x equals L has to be 0. So you might start to recognize that this is sort of analogous to another physical problem you've solved before, namely a standing wave on a string, where if you clamp the two ends of the string, the displacement of the string has to vanish at the endpoints. That is in fact very similar, and we'll keep on pressing on that analogy in the coming days. Okay, so the idea then is to apply this boundary condition to my general solution. So what happens is that, so let me draw an arrow here. So if I take that general solution and plug in psi is 0, right, so I have a sine 0 plus b cosine 0, and we just said that that has to be 0. Now, you know from trig that the sine of 0 is always 0, so that term vanishes entirely, because, and then now for this term, right, the cosine of 0 is always 1. So we know then that b equals 0 since cosine of 0 is 1. And lo and behold, we know from the boundary condition that this term here has to vanish. So I'll cross that out. So this is x that out due to boundary cond at x equals 0. We still, though, have to apply a boundary condition here to the remaining piece at x equals L, and that, it turns out, is where the fun starts. So our next step is to apply a boundary condition at x equals L, so that psi of L, we said, also has to vanish. So now, once we've killed off the term with cosine, we know that psi of L has got to be equal to a sine k L equal 0. So a is a constant, right? So, but if we set a to 0, then we're going to have psi, the whole wave function, be 0 everywhere. That's not going to satisfy normalization. So the only way, sort of the only physical way to satisfy this is for, this requires sine of KL to equal 0. So this now becomes sort of a math problem, namely, so we need KL, right? Sine of x vanishes at 0 and pi and 2 pi, 3 pi, etc. Or KL equals n pi, where n is an integer. This, it turns out, is what leads to our allowed discrete energies. So, but since K we defined as the square root of 2me over h bar, what we then have is we have, this means, so k times L, so root 2me over h bar times L equals n pi, or if we go and solve for the allowed values of E, so if I let's see, so I solve for E. Right. I'll do a little bit of the algebra. I think you can convince yourself that I'm gonna get an n and I get a pi and an h bar and an L downstairs equals 2m E. Since my energies E are going to be associated with an integer n, I'm going to label this as E sub n. I'll skip a step here, but I think you can see what I would do next. I'll just square this entire, both sides of this equation, and then I can divide by 2m. And this leads to my result, the allowed energies of an infinite squared well, E sub n equals n squared, right, this is h bar squared pi squared over 2m L squared. Okay, so let me write down the solutions, right? We know as well that the allowed wave functions, which I'm also going to label by n because, right, we know k is governed by a given value of n, right? So I'll label it as psi n of x are stationary states. That's going to be a sine KL. Now that K is going to end up, my A is going to end up being determined by normalization. I'm not going to go through the gory proof of that, but let me just keep this, I'll roll over to the top. So step 4, normalize. And I'll just write the answer down, right? So the full answer is that the full wave function looks like, oops, it's big, it is going to go like the square root of 2 over L times sine K, right? So which we know K has to be equal to n pi. N pi over L, sorry. Right, so it's KL that's equal to n pi. So for x between 0 and L. And the wave function vanishes otherwise. So in a sec, we'll go and cut to a computer, to my computer, where I can show you some pictures of the stationary states and of the spacing of the allowed energy levels. So there are a couple of things I wanted to say about the expression for the stationary state energies, the E sub n, that we had just worked out on the board. One thing to notice, so notice that the energy spacings aren't even. Well, first of all, we have discrete energy levels, which is a particular feature of quantum physics. In the case of the infinite square well, the energy levels are not spaced evenly as I go from n equals 1 to n equals 2, because of the n squared dependence here, I actually increase the energy by a factor of 4. And similarly for the other cases illustrated here. One other thing that is worth pointing out is that the lowest energy state is n equals 1. I think we might do it for a homework problem at some point. It turns out there's no solution to the infinite square well with n equals 0. So the lowest energy state, this n equals 1 state, has a non-zero energy. This energy is called ground state energy, and in the next class we'll talk a little bit more about the physical implications. Let's look now at the stationary state wave function. So here's my ground state where I've got sine pi x over L up to the normalization, so we get one bump between 0 and L. Our first excited state with n equals 2, we get another wiggle here, ditto for n equals 3. And from the wave functions, right, we can also plot the probability density, which is what we've got down here. And again, we will say a little bit more about the physical implications of these graphs next time, but I do want to point out, at least for the wave functions, the resemblance to what you've seen for standing waves on a string in Physics 217. This is really quite analogous to that. So we'll close with a clicker question. Please take a moment to think about this now. So hopefully you had a chance to think about it. So we had worked everything out in terms of k, right? Which so if the wave functions like up here go like sine kx, right? We can relate that k to the wavelength sort of within the well. And if you go and do the algebra for that and relate, so we know what the energies are in terms of over here. If you go and work this out, right, the wavelength in the well ends up being 2 pi over k, which ends up being related to the wavelength and the energy like this. And then, yeah, so the wavelength goes like 1 over the square root of the energy. So today we've worked out the allowed energies and the wave functions for an infinite square well. When we come back next time, what we'll do is to start to look at some interesting cases of time dependence where we have combinations of those allowed wave functions. See you then.